Mr. Cursey here. Now I'll be going over the solutions to the 2022 paper in some detail. So since this is a fairly long video, I've created headings for each question in the timeline below the video so that you can easily find the particular solution you're interested in. You should see the question numbers as you slide along the timeline. So let's begin the solutions. Here's question 1. Triangle ABC. We're given the three vertices of these points and we're asked to find the equation of the altitude through C. Now I'm going to use this diagram. Let's put in some of these coordinates. There's A, -1, -1. B is the point 2, -4. And C is the point 7, 3. Now, altitudes go from one vertex of a triangle at right angles to the opposite side. So this is a right angle. So we have to find the equation of that line. Remember, finding the equation of lines, you need to know a point on the line, which we certainly do. We know a point on that, and we need to know its gradient. Now, to work out the gradient of this line, we'll first work out the gradient of AB, because we know the line that we require the equation of is perpendicular to it. Remember, there's a wee result that when you multiply the gradients of two perpendicular lines, you get -1. So we know a connection between the gradient of AB and the gradient of the altitude that we're trying to find the equation of. So our first task then, in part A, is to find the gradient of AB. And we'll use the y difference divided by the x difference. So let's try the y difference of the two y coordinates, -1 minus -4, that's -1 plus 4. It's a y difference over the x difference. Now we started with this point, we have to start again with this point for the x difference. So -1 minus 2, just -1 minus 2. So we get 3 over -3, and we get a gradient of -1. That would be one along, one down, and that fits the diagram. It looks like that, so we're on the right track there. So from our result, this times the gradient of a perpendicular line would give us -1. 1 times -1 gives us -1. So the gradient of a perpendicular line will be 1. So we've found the gradient of the altitude. It's 1. And a point on the altitude, we're just gathering the information we need to use our straight line formula. Point on the altitude is, and it's 7, 3. So the equation of altitude is, and we use our y minus b equals mx minus a, where ab is a point on the line and m is the gradient. So it's y minus the y coordinate, 3, equals the gradient, it's 1, times x minus the x coordinate. So let's tidy this up. Y minus 3, we don't need the brackets here, we're multiplying everything by 1. And let's get the two constants together. I suppose we could take both variables onto the left hand side, so we get y minus x equals -4. So that's the equation of the altitude through C, part A. Let's look at part B next. We're asked to find the equation of the median through B. Now medians go from a vertex to the midpoint of the opposite side. So let's call that point M, and we'll say that. So let M be the midpoint of the line AC, the side AC. So let M be the midpoint of AC. So how do we find midpoints? Well, we know the coordinates of A and C, and it's an average. Mean of the X coordinates, mean of the Y coordinates. So M is, and let's show the calculation, the sum of the two X coordinates, -1 plus 7, halved. That's the mean of these two X coordinates. And we do the same for the Y coordinates, -1 and 3. So it's -1 plus 3 divided by 2. And that's easily simplified. So for the X coordinate, that's 6 over 2, which is 3. And for the Y coordinate, that's 2 over 2, which is 1. So there's the midpoint of AC. Now, can we work out the gradient of that median? Yes, we can, because we now know 2 points on that line. So the gradient of the line joining B to M, and again we use our Y difference over the X difference. So let's try 1 minus the -4, that's 1 plus 4, that's the Y difference, over, and we started with this point, so we start with it again, 3 minus 2. So it's 5 over 1, which is just 5. And therefore we've got all the information we need. So point on, let's just summarise what we know. Point on median is 3, 1, and gradient is equal to 5. So the equation of the median is y minus b, that's y minus the y coordinate, equals the gradient, 5 times x minus a, which is the x coordinate. Let's tidy that up. Y minus 1 equals 5x minus 15. And again, let's take all the variables on the left and the constants on the right. So it will be y minus 5x equals, add 1 to both sides, that's -14. So there's the equation of this median from B to M. Third part. Determine the coordinates of the point of intersection of the altitude through C and the median through B. So that's this point here. And we'd have the two equations to find this point of intersection, simultaneous equations. So we solve the system of two equations. There's the first one. Y minus x equals -4. And y minus 5x equals -14. So there's the two equations, and fortunately we've got the same number of y's in each equation. So let's subtract and see the magic work. So y away from y disappears. If we take away -5x, that's adding 5x from -x. So -x plus 5x will be 4x. It's -x, take away -5x. -4, take away -14, that's -4 plus 14. So that's 10. And divide both sides by 4. So we get x equals 10 over 4, which is 5 over 2. So we've found the x coordinate of this. That's 2.5. Now notice that there's 2 for B, 3 for M. Halfway between them is 2.5. That seems to make sense from the diagram. So to find y, let's use the first equation. It's the simplest one. Y minus x equals -4. So in this equation, we'll put x equals 5 over 2. So y minus 5 over 2 is equal to negative 4, which means y is equal to negative 4 plus 5 over 2. So that's negative 8 halves plus 5 halves. That's negative 3 halves. And so we can finally say the point of intersection is 5 over 2, negative 3 over 2. And just check that. We checked the 5 over 2. Let's check the negative 1.5. That looks pretty good because A's y coordinate is negative 1, so it'll be slightly below where A is. So yes, it all very much ties up with the diagram, and that's there for a sensible answer looking at the diagram. So there's question 1 solved. Well, here's question 2. We have an equation. It looks like a quadratic equation. It's got an x squared term, an x term, and a constant term. And we're told it has 2 real and distinct roots. That's solutions to that equation. And we have to determine the range of values for this constant p. So the theory behind this, you're aware that if you solve a general quadratic equation, ax squared plus bx plus c equals 0, that there's a formula that gives you the solutions, or the roots of that equation, plus or minus the square root of b squared minus 4ac all over 2a. So it's this choice in here. Let's just spell this out. You can either add the square root of b squared minus 4ac, or you can subtract it. And just looking at the expressions you get, you would imagine that you're always going to get 2 solutions, 2 roots. However, that's not the case, because suppose b squared minus 4ac was negative. The square root of a negative number is not a real number. That's going to get you into great difficulties, and you will get no solutions in that case. You might appear to have 2 solutions, but you've none. And what about having b squared minus 4ac being 0? The square root of 0 is 0, so we would have a plus 0 and a minus 0. We're not going to get 2 solutions. Each of these expressions will be identical. Adding 0, subtracting 0 makes not a jot of difference. In that case, we've got 2 coincident roots, or really 1 solution. So to get 2 solutions, you're going to have to be adding something and subtracting something. So the thing under the square root sign, this b squared minus 4ac, will have to be greater than 0. It can't be negative, it can't be 0, it must be greater than 0. So the discriminant, which is what that expression is, if that's greater than 0, then you will have 2 real distinct roots. If it's 0, you have 1 or 2 coincident roots, and if it's less than 0, you have no real roots. So that's the theory behind this. So let's compare the equation that we've got, 2x squared minus 8x plus 4 minus p equals 0. Let's compare that with this standard equation. So we'll compare it with ax squared plus bx plus c equals 0. And we can see that a is 2, b is negative 8, and c will be 4 minus p. So let's now look at the discriminant, because this is the crucial expression. So b squared minus 4ac will be negative 8 squared minus 4 times A, which is 2, times C, which is 4 minus P. Well, negative 8 times negative 8 is positive 64. 4 2s are 8, so that 8 is outside this bracket. We need to multiply that out, and we notice it's like a negative 8 multiplying both of these terms. So it's a minus 32. Negative 8 times negative P is positive 8P. So we're ending up with 32 plus 8P. That is the discriminant. So for two real distinct roots, the discriminant, that's the thing under the square root sign, has to be greater than 0. So 32 plus 8P is greater than 0. Let's take 32 from both sides. And let's divide both sides by 8. So this is the required range. So P can be any real number greater than negative 4. Otherwise, this equation will not have two real and distinct roots. So here we have question 3. We're asked to rewrite this trig expression of 4 sine x plus 5 cos x in this particular form, k sine x plus a, and we're given conditions on the values k and a, the constants k and a. So let's tackle this by expanding this expression. The addition formula would allow you to expand an expression like sine of x plus a, the pattern sine cos cos sine. So it would be sine x cos a plus cos x sine a. Now, the whole expression here is multiplied by k. The whole of this gets multiplied by k. Both terms get multiplied by k. And we compare that with the form we're trying to change. That's the 4 sine x plus 5 cos x. Now, this deserves coloured pencils out. The number times sine x, the coefficient of sine x, is 4. And up in this expression, which is identical to this one, the number multiplying sine x is k times cos a. That's the coefficient of sine x. They must be the same. So our first conclusion here is that k cos a, that's the coefficient of sine x up here, must be equal to 4, the coefficient of sine x down in this expression. So there's the first thing. Now let's do a similar thing for cos x. The coefficient of cos x here is positive 5. The coefficient of cos x here involves k times sine a. So these two coefficients must be identical. So k sine a, the coefficient of cos x in this expression, is the same as 5, the coefficient of cos x in this expression. So we have two equations with two unknowns, the k and the a. And two equations, two unknowns, that's enough to solve them and find what the constants are. But they're unusual simultaneous equations. They involve trig functions. But we can use various trig formulas. One of the trig formulas that we'll use is the fact that tan a is written as sine a over cos a. There's also another formula, and we'll also use it, that sine squared A plus cos squared A is equal to 1. So to get a sine A over cos A, we'll divide the second equation by the first equation. So k sine A divided by k cos A must be the same as 5 divided by 4. Now, why are we doing that? Well, we cancel out the factors k, top and bottom. We're left with sine A over cos A, which we know is tan A. So tan A is 5 over 4. Now, which quadrants are we in? Well, this is a bit unusual because we have a lot of information here. We know that k is positive. K is greater than 0. So positive times cos A equals a positive number. There's only one choice. Cos A must be positive. Similarly, k positive times sine A equals a positive quantity. Sine A also is positive. Now, which quadrant? Let's look at the quadrant diagram. Which quadrant has both sine and cosine positive? Well, it's the first quadrant. The sine's positive in the second, but cosine's negative. The cosine's positive in the fourth, but sine is negative. So A must only be in the first quadrant. That's the only possibility. So let's find out what A is equal to. And for that, we of course need a calculator. Now make sure your calculator is talking radians and not in degree mode. It should say somewhere radians as the mode. It's expecting to give answers and to receive angles in radians, not in degrees. So what angle has a tan of 5 over 4? So that involves this button. What is the angle whose tan is? Now on your calculator it may well be tan to the minus 1, but on mine it's a tan. Other calculators have arc tan, various designations. So what angle has a tan 5 divided by 4? Answer in radians, please. It's that. So A is equal to 0.896 and so on. So that's A. How do we find K? Well, we have recourse to this second formula. We'll square both of these. So if we square the left-hand side of the first equation, we get K squared cos squared A. And we'll add the second equation, left-hand side squared, k squared sine squared A. So this squared plus this squared must be the same as 4 squared plus 5 squared. Now, why are we doing that? Because look, common factor of k squared, we're left with cos squared A plus sine squared A, which we know is 1. And that all comes to, well, 16 plus 25, that's 41. So k squared times 1, which just gives me k squared, is equal to 41. So we know that k is the square root of 41. Now it's positive. Remember, we were told k is greater than 0. So I think we've mustered all the values that were required to rewrite this expression in the form k sine x plus a. So let's just write our conclusion that 4 sine x plus 5 cos x can be written as k root 41 times sine x plus, now it's 0.896 and the decimal went on, so we need to approximate this. So let's do it to 3 decimal places. Remember there was a 0 that would be chopping off. So there it is, and explain how you vandalised this number. You chopped it off to 3 decimal places. So that's part A completed. So let's move on now to part B. And part B asks us to solve 4 sin x plus 5 cos x equals 5.5 and gives us range between 0 and 2 pi for the value of x. Now this continues on therefore from what we've done in part A, where that expression 4 sin x plus 5 cos x was the one we worked on in part A. So we've done a lot of work on that. So let's replace that expression by the one we found in part A. So we'll have root 41 times the sine of x plus, and we revert to the full version. It's not an approximation we need now. So root 41 times sine of that angle is going to be equal to 5.5. That's what they're asking us to solve. So let's get the sine of that angle, the sine of x plus 0.896 and so on. Let's get that equal to 5.5 divided by root 41. Now we're saying that this angle is positive. The sine of this angle is positive. Now that happens in the first or the second quadrants. So let's make that observation, write it down. So the angle that we're dealing with, which is this angle, it's in the first or the second quadrants. Now let's deal with each in turn. So let's deal with the first quad angle. So there's the angle, and its sine is this value. So let's find that on the calculator. The angle whose sine is 5.5 divided by the square root of 41, and it comes to 1.033, 1.033, and so on. So that means that x in this case is equal to, well, it will be 1.033 and so on, minus, take away that from both sides. So it's minus that number. And that gives us 0.137, and it goes on 1 and so on. So there's one value for x. Now let's tackle the second quad angle. So there's the angle, and in this case we know that the second quadrant will be pi minus the first quadrant angle. So pi minus, and the first quadrant angle was 1.033 and so on. So let's figure this out. That would imply that x plus 0.896 and so on is the same as, let's work out pi minus 1.033. So there's pi button minus that number. So that now gives us 2.108 and so on. So we'll find x by subtracting 0.896 from 2.108 and so on. So we take this number and subtract 0.896. Now if I move up a bit, I should find it. There it is. Let's move back down. And that gives me 1.212 with a 3 after it. So x equals 1.212 and so on. So the solutions to this equation are 0.137, and I remember it was a small number we were chopping off after that, and 1.212, and again it was a number less than 5 we were chopping off. So these are both correct to 3 decimal places. And that's the two solutions between 0 and 2 pi for this equation. So here we have question 4, and we're given what looks like a cubic graph, and it certainly is that because there's a cubic expression for the formula for the graph, and we're asked to find the shaded area, first of all in part A, the shaded area above the x-axis. Now that would be calculated with a definite integral, and that would be the integral from -1, go from left to right. -1 is the lower bound and 2 is the upper bound, and we have to integrate the whole of x cubed minus 5x squared plus 2x plus 8. So the whole of that has to be integrated, and then we're going to plug these values in. We're going to get a number at the end of it because it's a area that we're asked to find. So let's first of all integrate this, and remember we put square brackets down, which in effect tells us that we're about to plug in values. So let's do the integration. Remember, it's increase and divide, so x to the 4 divided by 4 minus 5x cubed over 3 plus, now 2x squared over 2, the 2's will cancel and we'll get x squared. You check by differentiating back. If you differentiate x squared, you do get 2x plus, and the integrated constant, you get 8, that constant times x. If you differentiate back, 8x differentiated gives you 8. So there's the expression that we're about to plug in values, and in the first bracket we'll plug in the value x equals 2. In the second bracket we'll plug in the value -1. So let's go ahead and just do that substitution. So we'll get 2 to the 4 divided by 4 minus 5 times 2 cubed divided by 3 plus 2 squared plus 8 times 2. So there's the substitution made. And we'll do a similar substitution with -1. So we've got -1 to the power 4 over 4 minus 5 lots of -1 cubed over 3. And then we'll have a -1 squared, and then an 8 times -1. So calculations next. Now you hopefully have calculators with fraction facilities on it. We wouldn't do that yet. We must make this a lot easier for our calculator. This is a horrendous calculation to do straight away on your calculator. So let's attempt to do some mental simplifying first of all. And on the top of this first fraction we've got a 2 times a 2, which is 4, which will cancel that 4, times another couple of 2's. So that'll come to 4 altogether. It's 2, 4, 8, that's 16 over 4. So there was a bit of cancelling there. On the top of this we've got 5 times 2 cubed is 8, 5 eighths are 40, so we've got minus 40 thirds. We've got a plus 4, and we've got a plus 8, that was times 2, wasn't it? So that's 16. So there's the first bracket, and that looks healthy for substituting into your calculator should you have fraction facility on your calculator. Let's work out the second bracket. Negative 1 to the power 4, that's going to be a positive answer, and it's just going to be 1. So it's 1 over 4, 1/4 for the first term. Now negative 1 cubed is negative 1. With this negative makes this term positive. 5 times 1 is 5 over 3. So there's 5/3. And this term, negative 1 times negative 1 is plus 1. And this term, 8 times negative 1 is negative 8. And there's the second term. So you launch yourself into the calculator. I would work out each bracket separately. Now, unfortunately, my on-screen calculator does not have fraction facility, so I'm just going to plod on with this and do it in my head. So I'm looking at 4 plus 4, which is 8, plus 16 is 24. So I've got 24 minus, I'm also looking at thirds and quarters. I'm going to change this into twelfths by multiplying top and bottom by 4. So that's 160 over 12. And I've taken care of these. Now the second bracket, the 1 minus the 8 is negative 7. With this negative, there'll be a plus 7. And then twelfths here, this multiply top and bottom by 3, that'll be 3 twelfths plus 20 twelfths. So that's 23 twelfths, and I'm subtracting it, so that's minus 23 twelfths. So I'm certainly making progress here. I don't know how you're getting on with your calculator. We'll meet at the end of the question and then see if we can agree. So 24 plus 7 is 31. And then let's gather the twelfths together. We've got a minus 160 of them, minus another 23 of them. That's minus 183 twelfths. Now I'm looking at the 183 and the 12 and thinking 3 cancels. So 3 goes into 183 61 times, and 3 into 12 goes 4 times. So that's looking a lot healthier. So I've got 31 minus, and I'm going to change this into a mixed number. 4 into 61 goes 15 1/4. If I take 15 from 31, I get 16. I've still to take away that quarter. So I'll get 15 3/4. Now that is the area, the exact value of this area. So it's units squared. We'll always measure area in square units. So that's my first calculation, 15 3/4 units squared. So let's now move on to part B. And it says, hence calculate the total shaded area. So we have to calculate this area and add it to the area that we've already calculated. Now the negative of that area will be given by, remember it's below the x-axis, so if we work out the integral from 2 to 4 of the function x cubed minus 5x squared plus 2x plus 8, that will not give us the area, that integral, but the negative of the area, which is why I've got negative area at the front there. But there we go, and we've already worked out what we get when we integrate. We get x to the 4 over 4 minus 5x cubed over 3, and there was a plus x squared and a plus 8x. And this time we have to plug in a 2 and a 4 to find out what goes on. So let's continue with this. I've got 2 brackets now. And in the first one, we're going to substitute 4. So we get 4 to the power 4 over 4 minus 5 times 4 cubed over 3 plus 4 squared plus 8 times 4. So that's just that substitution. And for the second substitution, we're putting in x equals 2 into this, which I think we've already done in this bracket. So let's just copy down the substitution that we had already. I'm going to that form of it there. So let's try the first bracket and simplify it. 4 4's multiplied together and 1 4 on the bottom. One of them will cancel and get 4 cubed, which will be 64. Minus, well, this one, 4 4's are 16, 4 16s, that's 64 times 5. We'll deal with that in a minute. And we divide that by 3. Plus 16 plus 32. And then we have to subtract this second bracket. Let's look at that. We've got a 4 plus 4 is 8, plus 16 is 24. We're subtracting that. And then the fraction, we're subtracting negative 40 thirds, so that's adding 40 thirds. So again, we're making good progress here. So let's deal with all these constants. 32 minus 24 is 8, and 16 is 24. Added on to 64 is 88. And then we've got minus, well, how many thirds do we have here? 4 plus 25, 6 is 30, 320. So there's minus 320 thirds. We've taken care of all of these, and a plus 40 thirds. So 88, and then we take 40 from the 320, that will give us 280. It's negative 280 thirds. And let's divide out. 3 9s are 27, and 3 1/3. So we are getting a negative value, which is useful. So let's take away 93 from 88. That's negative 5. And then we've still to take away 1/3. And this gives us negative 5 1/3. And we said that was the negative of the area. So the area below will equal 5 1/3 units squared. Now we're asked for the total shaded area. Let's tackle that. Total area will be the sum of the two areas we've found. That's a 15 3/4 plus 5 1/3. So 15 and 5 gives us 20. Let's think twelfths for this lot. That'll be 9 twelfths plus 4 twelfths. That's 13 twelfths, which is 1 1/12. So we're ending up with 21 1/12 units squared for the total area shaded in this diagram. Well, here's question 5. Given a couple of functions f and g in their formulae, and we've to find expressions for these. So let's start with f of g of x. So first of all, we know what g of x is. No problem with that. It's 3x plus 5. So there's a first step on the way. So into the function f, we're putting 3x plus 5. Now, what does the function f do? When x goes in, it squares it and takes away 2. So, for instance, if a goes in, it'll square it and take away 2. If b goes in, it'll square it and take away 2. If squiggle goes in, it'll square squiggle and take away 2. Now, in this case, we're putting 3x plus 5 in. So it'll square 3x plus 5 and take away 2. So that's our next move. 3x plus 5 squared, take away 2. Now we can multiply this out. Something squared, it's multiplying it by itself. It's got a couple of linear expressions multiplied. That's a case of first outsides, insides last. So the first two terms will give us 9x squared. The outside 2 gives us 15x. The inside 2 give us 15x. That's 30x. And the lasts, 5 times 5 is 25. And we take 2 away, we'll get 23. So there's a nice, healthy quadratic expression for f of g of x. And along similar lines, let's look at the second one, which is g of f of x. This is a composition of functions. We're doing f composed with g, g composed with f. We'll swap the order around in this case. So a similar strategy goes on. What is f of x? It's x squared minus 2. What are we putting into g? We're putting x squared minus 2 into g. We have to decide what does g do when numbers go into it. When x goes in, x is multiplied by 3 and 5 is added. So for instance, if a goes in, 3 times a plus 5. If b goes in, 3 times b plus 5. If squiggle goes in, 3 times squiggle plus 5. And in this case, what is going in? It's x squared minus 2. So there's our answer to that part. We do 3 lots of x squared minus 2 plus 5. And that can be simplified. 3x squared minus 6, 3 lots of negative 2, minus 6 plus 5 is minus 1. And again, a quadratic expression. So let's have a look now at part B. Part B asks us to determine the range of values of x for which this expression is less than that expression, and we've worked out part of this. So we basically have this quadratic expression, 9x squared plus 30x plus 23, that's f of g of x. It's to be less than g of f of x, which is 3x squared minus 1. So we're into quadratic inequation territory. Let's subtract 3x squared from both sides and also add 1 to both sides. Let's divide both sides by 6. So everything gets divided by 6 here. So we've got to find the values of x which give x squared plus 5x plus 4, which make that less than 0. Let's do one other thing here, and let's factorise x squared plus 5x plus 4. That's a straightforward one to factorise. We get that. Now, suppose x plus 4 times x plus 1 was actually equal to 0. Then we know either x plus 4, 0 or x plus 1, 0, in which case x would be equal to negative 4 or negative 1. Now if I sketch a graph of y equals x squared plus 5x plus 4, we know it's a quadratic graph with a positive x squared, so it's that way up, not the inverted way. That would be if it had a negative x squared term. So it's this one, and it crosses the x-axis when this is equal to 0. We've just solved that. It crosses the x-axis at negative 4 and negative 1. So the graph is a parabola crossing the x-axis at negative 4 and negative 1. And now I've got all the information I need to solve this final question, because it's asking when are the values of x squared plus 5x plus 4 less than 0? When on this graph is y, that's the heights of the point, when are they less than 0? Well, that happens on the graph down here. All these points from negative 4 to negative 1 for x are below the x-axis and therefore negative. So the range of values x lies between negative 4 and negative 1. And if that's the case for any x value in here, you work out y, you'll get a negative answer. Now we're not allowed negative 4 and we're not allowed negative 1, because in that case the values of x squared plus 5x plus 4 are actually equal to 0. Anywhere else, if they're less than negative 4 or greater than 1, y values are greater than 0. And x squared plus 5x plus 4 would be greater than 0. So the range of values required is between negative 4 and negative 1. Well, here we have question 6. We have a curve with the equation y equals f of x. We're told that dy by dx equals 1 minus 3 over x squared, where x is greater than 0. And we're told that the curve passes through the point 3, 6, and we're asked to express y in terms of x. So the problem here is how to interpret this question. What does it mean when we're given a formula like this for dy by dx? Now remember, dy by dx is basically the gradient on a curve. So what we're being given here is the gradient formula for a curve y equals something. So this is the gradient formula. So we have to, from this, try to figure out what the actual formula for the curve is. So we're trying to go not from y to dy by dx, which we know is differentiation. We differentiate to do that, to find the gradient. We're doing the reverse. We're going from being given the gradient formula to get back to try and find the curve formula. And going from dy by dx back to y is the inverse process to differentiating. It's integrating. So we would have to integrate our gradient formula. So to recover y, that's the curve formula. That's the curve that has this as its gradient. We integrate. Now it's not in a state we can integrate. We've got 3 over x squared. Remember, integrating, you have a formula that allows you to integrate powers of x by increasing and dividing by the new power. Remember, we have a plus c. We'll talk about that in a minute. So integrating this, if we integrate this, we have to rewrite this first of all, prepare it for integration. This x squared down in the bottom nips up to the top of the fraction to join the 3, and the power 2 becomes negative 2. So that's now in a suitable form for integrating. If we integrate 1, we get x. Check, by differentiating x, you get back to 1. And integrating this, we'll have a negative 3, it just still sits at the front. Increase the power by 1, that gives you negative 1, and divide by the new power. And we need a constant of integration. So let's tidy this up. We've got x minus, and this negative 1 here, 2 negatives, we are plus 3x to the minus 1 plus a constant. And finally, let's just write this as a fraction, so the x to the negative 1 goes down to the bottom of the fraction and becomes x to the positive 1, so that's just x. So we're ending up with a curve, y equals x plus 3 over x plus c. Now, we don't know what c is. This is a whole host of curves. Let's have a wee look at this set of curves, or family of curves, and just talk about their gradient, because all of these curves, no matter what c is, should have the same gradient formula. They should have the same gradient. Let's look at that. So here we have a graph of y equals x plus 3 over x plus c, and in this case c is 0. Now, it's not a graph you're really familiar with. It seems to have 2 branches, one up here and one down here. That's not the point. The point is that this graph, along with adding 0.9, all of these graphs, there's a whole host of them, all with different values for c, all of these graphs seem to return the same gradient formula. Now, it's not at all clear that that's what's going on, that each of these graphs, this one, this one, this one, all have the same gradient. If we concentrate on x equals 1, for instance, there's a line where all the points in that have x equals 1, and look at the gradient of the graphs as they cross that line. They should all be the same. That blue graph, where it crosses the pink line, the gradients should all be the same. It becomes even clearer if we draw in the tangent at these points. You can see the tangent, all these tangents have the same gradient. So no matter which curve we stop at, when x equals 1, the gradient of the tangent is always the same. So all of these, this happens all along this blue graph, all of these graphs will return exactly the same gradient formula. Now, if we go back to our question tells us that the particular curve that we're looking for passes through the point 36. Now, there's a hosts of curves that we get, all of which have this for the gradient formula. Only one of these is going to pass through the point 36. So let's go back to our demonstration and see if we can find it. And look at the point 36 in particular. So here's the curve y equals x plus 3 over x plus 0. And let's have a look at this point 36. There it is. Now, as we change the value of c, and we want the curve to pass through the point P. Well, there's one. If we go any further, it misses. And it would appear from this demonstration that the value of the constant c that we're after is 2. This particular curve passes through the point 3, 6. So let's go back to the question and see if we can work out and prove the fact that c equals 2 for the curve to pass through the point P. So here's the curve we're looking at. However, we do know, therefore, that 3, 6 lies on this curve. Now, for that to be true, when x equals 3, y equals 6. So let's substitute values. So we know therefore that 6 will be 3 plus 3 over 3 plus c. And that means 6 is equal to 3 plus 1 plus c. That's 4 plus c. And take 4 from both sides. We've discovered that c does indeed equal 2. So express y in terms of x. Y will equal x plus 3 over x plus 2. It's that one particular curve that happened to pass through the point 3, 6, as we saw on the demonstration. So here's question 7. We've got two variables x and y, and they're connected by an equation of this form, y equals kx to the power n. And we've defined values of k and n. The only information we're given is that the graph, or the relationship between log to the base 5 of x and log to the base 5 of y, is a straight line graph passing through these 2 points. So, first of all, let's look at a more familiar normal, we'll call it the normal setup, which is not this one, not the one we're looking at. And that's where we've got an x and a y variable passing through 0, 3, that's the y-intercept, and a point 2, negative 1. Now, in a normal setup like this, we would use the fact that the equation is y equals mx plus c, where, remember, m is the gradient of the line and c tells you the y-intercept. So we have the y-intercept 0, 3, we don't have the gradient, so let's figure out the gradient. That's the y difference, that's the 3 minus the negative 1, over the x difference, 0 minus 2. And that's 4 over negative 2. So the gradient on this line is negative 2. So the equation, this is in the normal setup where we have an x and a y relationship being a straight line graph passing through these 2 points. The equation is, in this case, y equals negative 2x plus and 3 for the intercept. So that's fine, but that's not the situation we've got. What we do have is a relationship between log to the base 5x and log to the base 5y. So at this setup, which is different from the normal setup, we would have log to the base 5 of y equals m log to the base 5x plus c. And we would work through all this and end up with this equation. So in this case, the equation is log to the base 5 of y equals negative 2 log to the base 5 of x plus 3. We're replacing x up here with log to the base 5 of x and y up here with log to the base 5 of y, and just doing the same nonsense that we did up there. Find the gradient and we know the intercept. So we've ended up with this being our equation. Now this looks a far way away from the equation that they tell us is the relationship between y and x. So let's have a look at the equation that they've got. So let's consider now the equation that they tell us is the relationship between y and x. It's of this form. But we've ended up with a relationship like this. So somehow we have to move from this one to this one. And one of the ways that we can do that is to take the log to the base 5 of both sides of this equation. If y equals this, then log to the base 5 of y will equal log to the base 5 of k times x to the power n. Now, the laws of logs tell us various things, and it tells us, the laws of logs tell us that if we have the log of a product, multiplying two numbers, then we add the logs. So in this case, we'll have log to the base 5 of k plus log to the base 5 of x to the power n. And another law of logs would tell us that this power here can drift down to the front. So we can keep going with this because we're getting very close to this. Log to the base 5 of y is equal to, and let's do this term first, bring the n down to the front, n log to the base 5 of x plus log to the base 5 k. So get the coloured pencils out, we'll look at these two and compare them. You'll notice that there's -2 as the coefficient of log to the base 5 of x. The coefficient of log to the base 5 of x down here is n. And up here the constant at the end is +3, +3. The constant here is log to the base 5 of k. So these coefficients there must be equal, these constants there must be the same. So finally we can say that we have established that n is -2, and also that log to the base 5 of k is equal to 3. Now this is a log statement. Every log statement can be written as a power statement. I like to read these as saying, what power do you raise 5 to get k? Answer's 3. So we'll get k by raising 5 to the power 3. That's 5 times 5 times 5, it's 125. So we've established the two values that we were required to find. N is -2 and k is 125. So here's question 8, where we've got a diagram of a plot. The plot contains a pond surrounded by a path, and we're given all the various measurements, and in part A we're asked to find an expression, this expression for the area of the pond, and that depends purely on the variable x. And you'll notice in the diagram the plot has dimensions x times y. So let's look at this part A. And the first thing we'll do is find the area of the pond from these dimensions. So the breadth, first of all, breadth of pond, and we do the best from the diagram. So this side of the plot is y, all in meters, y meters. These two path widths are 1 meter each. That's 2 meters. So to get this breadth of the pond, we'll take y meters and subtract 2 meters from it. And the length of the pond in a similar manner, this length here, well, it's x minus a couple of path widths, and this time is a couple of 1.5 meters. That's 3 meters altogether. So it's x meters minus 3 meters, x minus 3. So that's the two dimensions of the pond. So we can now say that the area of the pond is the length times the breadth. That would be x minus 3 times y minus 2 square metres. Now, unfortunately, that's got y in it, and we're asked to find an expression that contains only x as the variable. So this y has to disappear somehow. Now let's look at the information we're given. All of this information involves what's seen on there. However, this extra piece of information, that the total area of the pond and the path together is 150 square metres. Now the area of the pond plus the area of the path actually gives you the area of the plot. So let's write this down. Area of plot is the area of the pond plus the area of the path. And we're told that that's 150 metres squared. Now the area of the plot we know is x times y. We're told the dimensions of the whole plot, x times y. So x, y is equal to 150, and this gives us the opportunity to find y in terms of x, because if we divide through by x, y we discover is 150 over x. And that means we can now go and find an expression for the area of the pond in terms of x, which is what what's required. So it's there, the length of the pond is that. We now know the breadth of the pond will be 150 over x. We're replacing y by that, minus 2. And we're in a classic first outsides, insides, last situation here. Let's work that out. The first, x times 150 over x, the x's cancel, we're left with 150. The outside 2, minus 2x. The inside 2, that's minus 3 lots of 150 over x, that's minus 450 over x. And lasts, negative 3 times negative 2 is plus 6. So finally, if we simplify that, it's 150 plus the 6, minus 2x, minus 450 over x. And that's precisely what we were asked to show. So that's part A completed. Let's have a look at part B. We're now asked to determine the maximum area of the pond. So if we were to show a graph of the area which depends on x, to get a maximum area we'd be looking at a graph where it would come up to some sort of turning point. In other words, a stationary point in the graph of y equals a of x. So we'll be looking for stationary points on this graph. So this would involve differentiation. We find stationary points by finding where the gradient on the graph is equal to 0. The tangent is horizontal, it's parallel to the x-axis, 0 gradient. So let's differentiate first, and we certainly aren't in a state to differentiate it because of this last term. We would have to prepare that for differentiation and bring that x to the power 1 up to the top of the fraction to join the 450. And that would be an x to the minus 1. That's now in a state where we can differentiate it. So we can go ahead with that. If we differentiate a constant, we get 0. If we differentiate negative 2x, we get negative 2. If we differentiate this, we multiply by the power. That's negative 1 times negative 450. That's plus 450. And then take 1 away from the power. That'll be negative 2 for the power. So let's just write that as a fraction, and that negative power will that'll drift down to the bottom and become a positive power. So it's 450 over x squared. So for stationary points, or stationary values, we'll set the gradient on the graph, a dashed of x, to be equal to 0. So we're solving negative 2 plus 450 over x squared equals 0. Now, let's multiply through by x squared. All terms get multiplied by x squared. And let's add 2x squared to both sides. Get 450 equals 2x squared. So therefore, 1x squared divided through by 2 will be 225. Finally get to the value of x. It's either plus or it could be minus the square root of 225, plus or minus 15. However, let's think about the negative value. If we look at this diagram, x is the length of the plot, and x is a measurement. X will be greater than 0. So we'll say x has to be greater than 0 because it's a measurement. So x equals 15 is the only valid solution. Now, we don't yet know whether this does give us a maximum value for the area or not, and we'd have to do a little bit of analysis on that. We'd have to take values of x around about 15, for instance less than 15 and greater than 15, and we'd have to examine whether the gradient, that's a dashed of x, is positive or negative in these various areas. Now we know that when 15 goes in to the expression for a dashed of x, now I'm going to be using this expression up here to make my arguments. 15 in there, 15 squared is 225, 225 into 450, that gives us 2 there. And obviously negative 2 plus 2 is 0. We knew that when x is 15, the gradient is 0. This expression here is exactly 2. Now if I go to the left along a number line, if I make the values of x smaller than 15, then this will be smaller than 225, and when I divide it into 450, it will be larger. I'll get larger answers than 2. So I'll get a larger number than 2, subtracting 2. That'll be a positive value I'll get for the gradient. And likewise, if I go to numbers greater than 15, then this will be greater than 225, and it will go into 450 less than 2 times. So we get a number less than 2, and we're subtracting 2 from that, we'll get a negative value. Now what does that mean? This is the gradient, so the shape of the graph, which would be y equals a of x, if we were to graph the values of the area of the pool, we'd get a upward graph, stationary point, and then a downward graph. So this is evidence that x equals 15 gives a maximum value for a of x. And what is that value? Well, let's try and find it. So let's now put 15 into the formula for a, and I'm going to use the factorised version up here. It's easier to calculate. X minus 3, so that's 15 minus 3. In the second bracket, 150 divided by x, so it's 150 divided by 15, and we subtract 2 from that. So the first bracket gives me 12. The second bracket, 15 into 150 is 10. 10 minus 2 is 8. 12 times 8 is 96. So we can now happily say that the maximum area of the pond is 96 square meters. And we've proved it's a maximum using this table of signs, as it's called. So here we have question 9. We're told that there's a line given its equation and it intersects a circle at the point P and Q, and we're shown the diagram. There's P, there's Q, the 2 points of intersection. Now remember, at points of intersection, the coordinates of these points satisfy both the line equation and the circle equation. So these two equations have to work at the same time. In other words, it's a simultaneous equation. Therefore, we would be solving that system of equations. So y equals 3x plus 7 and x squared plus y squared minus 4x minus 6y minus 7 equals 0. So that system of equations, the two must work together. So this is true and also this is true. So what we would do is we'll let y equals 3x plus 7 in the circle equation. So we'll replace y by 3x plus 7 into the circle equation. And that gets rid of y in it and leaves us with only one variable in an equation, which is we're then able to solve that equation. So let's continue with this. So x squared plus, now we're saying y squared gets replaced by 3x plus 7 squared minus 4x minus 6y. Well, not y, we have to replace that by 3x plus 7. So it's 6 lots of 3x plus 7 minus 7, and that equals 0. So it's quite a complicated thing. We'll better multiply that out. So this therefore gives us x squared plus, now 3x plus 7 all squared, that will become 9x squared plus 42x plus 49. You do your first outside lasts if you want to do the working. First outsides, insides last, and you'll get 9x squared plus 42x plus 49. And we're minusing a 4x. We've got a negative 6 outside these brackets, so it's minus 18x minus 42 minus a 7 equals 0. So let's tidy up this, what appears to be a quadratic equation in x. We've got 10x squared. X terms, there's 42 minus 4, that's 38, minus another 18, that's 20. So 20x. Then constants, 49 minus 42, 7 minus 7. Well, that gives you 0, so the constant term disappears. And this is a neat little equation. There's a common factor of 10x in there, leaving x plus 2. So we've got 10 times x plus 2 equals 0. So either x is 0 or x plus 2 is 0. So if x plus 2 is 0, x would be negative 2. So we've got two possible solutions. We've got x equals 0 or x equals negative 2. So two values that give this expression a value of 0. So let's take each one in turn. So we'll let x equals 0. Now we know that y is 3x plus 7, So let's plug in x into that. Y is 3 times 0, therefore, plus 7, which gives us 7. So what have we discovered? That when x is 0, y is 7. And looking at this diagram here, x is 0, x is negative 2, q is the one with the largest x coordinate, so further to the right. So q would be the point 0, 7. And we'll put that up here, 0, 7. And let's tackle the second value that we found, negative 2. So what would y be in this case? It would be 3 times negative 2 plus 7. Well, that's negative 6 plus 7, that's 1. So the other point on this diagram, the point P, will be negative 2, 1. Negative 2, 1. And the heights check out. This is a height of 7, this is a height of 1. So we've identified the correct points. So that's part A completed. We've found the coordinates of P and Q. Let's move on now then to part B. What are we asked in part B? We're told that this line, the one we were dealing with here, is a tangent to a second smaller circle which is concentric. It shares concentric. It has the same centre as this original circle did, and we have to determine the equation of the smaller circle. Now let's remind ourselves of equations of circles. If we have a centre of a circle being AB and the radius of a circle being R, then the equation is x minus a all squared plus y minus b all squared equals r squared. So that's one of your well-known formulas. So what do we know about this smaller circle? We certainly can work out its centre because it's the same centre as this circle. So let's work out that. So if we consider the larger circle equation, that's x squared plus y squared minus 4x minus 6y minus 7 equals 0, then we know if there's a 1x squared and a 1y squared, we can read off the centre by looking at the x term coefficient and the y term coefficient, half them and change sign. So the centre is, let's call it C. So half of this negative 4 is negative 2, change sign will give us 2. Half of this negative 6 is negative 3, change sign, that will give us 3. So the centre appears to be 2, 3. So let's put that on this drawing. And let's also include the information we got from the original calculations in part A, where we worked out the coordinates of these points. Now, it may well be worthwhile finding where the axis is on this diagram. Let's hunt down the origin. If this point has a 0 for x and negative 2 is the x coordinate here, the origin will be somewhere on a vertical line through Q. Its x coordinate is 0, and a height, this has a height of 1, this has a height of 7, so the origin must be sitting down here somewhere. You could put in pencil, you could roughly put in axes where the origin is roughly down there. So there's negative 2, 1 for P, 0, 7 for Q, and 2 along, 3 up for the centre that we've just found, 2, 3. So everything seems to be right. Let's just keep these axes there because it gives a double check to what we're finding. So the centre is 2, 3. how do we find the radius of this smaller circle? Well, it's all to do with this being a tangent. And there's a lovely symmetry in the two circles with this tangent. There's an axis of symmetry which goes through this centre and out the other side. There's an axis of symmetry. And you'll notice that there's a straight line going from the point of contact to the centre, and that's the radius. This is the midpoint, because it's an axis of symmetry. That's the midpoint of the line PQ. Therefore, if we find the coordinates of M, we know the coordinates of C, we can therefore work out the distance of M from C, and that'll give us the radius of that smaller circle. So let's write this down and explain what we're doing. Let M be the midpoint of PQ. That's the chord of the circle, and it's the tangent of the smaller circle, chord of the large circle, tangent to the smaller circle. Let M be the midpoint of PQ. So what are the coordinates of M? Well, we take the average, the mean of the x coordinates, add them up, divide by 2, so it's -2 plus 0 over 2. And we do the same for the y coordinates, 1 plus 7 divided by 2. And that's easy to calculate. This will be -1 and 4. Check on your diagram that that does make sense. I'll put -1, 4 in there. There's the origin. 1 to the left, 4 up. Seems reasonable. So that's the midpoint. A radius, therefore, a radius of the smaller circle is that line joining M to C, is MC. And let's work out the distance from M to C. That'll be the distance formula, the x difference squared plus the y difference squared. Let's look at the x difference squared. -1 minus 2. Let's look at the y difference. 4 for the y coordinate minus 3. So we've got the square root of, that's -3 squared, that'll be +9, plus 1 squared, that's 1, so it's square root of 10. So what do we know about this smaller circle? So the centre we've found is is 2, 3. It's the same as the centre of the large circle, and the radius, I'm just gathering the facts that we need, the radius is square root of 10. So we've finally found that the equation that we were asked for, the equation of the smaller circle, is, and remember we're using this form of the equation of the circle. So it's x minus the x coordinate of the centre, that's 2, x minus 2 squared, plus y minus the y coordinate of the centre, that's 3, and the radius squared. Well, the square of root 10 is just 10. So there's the equation of that smaller circle. Now you may do checks if you want to. It's interesting that the circle looks like it just crosses the x-axis there when y equals 0. If we put y equals 0 into this equation, I'm just doing a brief check just to see if everything's reasonable. You don't have to do this. You can just accept that that's the answer. It's always nice to check if you possibly can. So we check if y equals 0 and put that into this equation. We'll get x minus 2 all squared. 0 minus 3, that's negative 3 squared, that's 9. If we take 9 from both sides, we'll get a 1. So it would imply that x minus 2, if we take the square root of both sides, positive or negative, is plus or minus 1. That would give us the values of x of 2 plus 1, which is 3, or 2 minus 1, which is 1. That looks pretty good. There's a 1, there's a 3. So it's a double check. It would seem to be reasonable that the x-axis cuts this smaller circle at 2 places. So I've used the equation we've got to derive something that looks reasonable on the diagram. It's just a wee extra check. Not necessary, don't worry about that. So that's our final answer. X minus 2 all squared plus y minus 3 all squared equals 10. Well, here's question 10. We've got a heptathlon event at an athletics contest, and we're told that in the 200-metre event that this formula gives us a way to calculate the points for each contestant, where t is the time that the athlete took to run the 200 metres measured in seconds. And we're asked to calculate how many points would be awarded if the time recorded was 24.55 seconds in this event. So let's tackle this, and we'll look at the formula first. To get the number of points, we take 4.99087 and multiply the difference between 42.5 and the time taken raised to the power 1.81. A bizarre formula. So this is the number of points awarded, and this is the time in seconds. You always got to watch out in these things about the units that are used, just to see that we don't have to do any conversions. So that's the time in seconds. So we're asked to calculate the number of points when the time was 24.55. So in this case, the points awarded would be this calculation, this 4.99087 multiplying 42.5 minus the time taken, which we were told was 24.55, and we raise that to the power 1.81. So this obviously requires a calculator. We'll not do this in our heads. So let's try this. So it's 4.99087 times, and brackets go down, and inside the brackets we've got 42.5 minus 24.55, and we're raising that. Now in this calculator it's y to the power x. You might well have just a wee hat sign on the key on your calculator, and it's 1.81. So that's raised to the power 1.81. Press the button and there we have the answer. 929.036. Now let's be realistic here. Presumably when points are awarded to a contestant, we don't bother about fractions of a point. So the points awarded are, be to the nearest whole number, 900 awarded are 929. So that's part A. Let's get rid of that. And now we're on to part B. And here's another bizarre formula. And this is for another of the events in this heptathlon. This time it's the long jump event. So let's look at this formula, 0.188807 times, and this time it's the difference between D and 210, and it's raised to, well, we don't know what the constant is. It's just a constant. So again, this is the number of points. This time, this is the distance. It's a long jump, measured in centimetres. And this is a constant. And the question asks us to find that constant. We're told that 850 points were awarded. The jump was 6 metres, 600 centimetres. So let's go ahead. Again, we can just plug in values. So in this case, 850 is equal to 0.188807. The distance jumped was 600 centimetres. Was to subtract 210 and raise it to this quantity. So that constant is the only thing we don't know in all this. Let's do one final simplification in this, which is the bracket at the end. So 0.188807. Now 600 minus 200 is 400, take away another 10 is 390. So this is 390 raised to the power k. So how are we going to do this? Well, let's first of all divide both sides by 0.188807. At least then we'll have just the one number on what I'm making the right hand side of the equation. So basically we're sitting looking at a power statement, like for instance 10 squared equals 100. And all power statements have a log statement, equivalent log statement. And in this case, log to the base 10 of 100 is equal to, what power do you raise 10 to get 100? The answer is 2. Now we would get that, one way of getting that is to take the log of both sides. This is log to the base 10 of both sides. And we know that 2 comes down to the front, would get twice log to the base 10 of 10 is equal to log to the base 10 of 100, and we would therefore find that that 2 is equal to log to the base 10 of 100. Now why am I doing all this calculation? Because 2 is the power. 2 is the wee power up here, and I've got that in terms of the 100 and the 10 by taking log to the base 10 of both sides. I could equally do that here. I could take the log to the base 10 of both sides. Equally well, I could take log to the base e of both sides. Doesn't matter, so long as when I take the logs of both sides, I have the same base. So I'll choose to do log to the base 10. A bit tedious writing all this down, but necessary. And then I'll mimic what I did down here. I'll bring that k down to the front. So it's k times log to the base 10 of 390, and then I'll divide by the log to the base 10 of 390, just like I did here with the log to the base 10 of 10. Incidentally, log to the base 10 of 10 is 1, giving just the log statement. So here I've got log to the base 10 of 850 over 0.18887 divided by log to the base 10 of 390. Now that's something I can do on the calculator. So let's do it. There's the log button. and it's 850 divided by 0.18887. So that's the top of the fraction. I have to divide that by log of 390 and press the button. Well, I haven't completed. There's log to the base 10 of 390. Press the button, there's our answer. It's 1.40999998 and so on. Now, usually you're told when you approximate in a question to look at the data that you're already given, and I'm given in this something that's correct up to 6 decimal places. Maybe I should round this to 6 decimal places and chop that 8 off, in which case all of this would become 10000. So it's 1.410000, and that's to 6 decimal places. It'd be perfectly acceptable for you to write 1.41 down, correct to 2 decimal places if you want. But there we go. It's 1.410000. That's the value of K. That's Mr. Corsi signing out. Hope you enjoyed the video.